And our objective today is to learn about the sums of random variables. Now, sums of random variables is an important concept because, I mean, summation is one of the basic arithmetic operations, right? So, you are basically summing up everything, many things. Okay. For example, if you want to take the average of a sample, let's just say you have 10 observations about a certain procedure or certain event, and you have 10 different observations and you would like to take the average of them. So let's just say you are making an experience in the experiment in the physics lab, and in that experiment you have come up with 10 different results. And of course, in order to make a comment, you are going to take the average of these results, right? And in order to take the average of these results, of course, you first need to sum them up, then divide to the number of results. So even when you are taking average of values, you are basically summing them up first. So summation is an important operation even for the random variables, and sums of random variables has an essence. Therefore, we need to understand this concept, how we are going to model the sums of random variables, because sums of random variables are also random variables as well. So if you have, for example, two random variables, most probably their sum is also going to be a random variable as well. And therefore, first we are going to study the expected value of the sums of random variables. Then we are going to learn new concepts such as covariance and correlation. We are going to learn about these new concepts. And when the time comes, I'm going to explain what does a covariance and correlation measure. Okay, so they indicate what? These values, the covariance and correlation, they indicate what? We are going to explain this in this section. And then, since we have started with the expected value of the sums of random variables, we are going to continue with the variance calculation for the sums of random variables. Now, why do we put this covariance and correlation topic in the middle of these two topics? I mean, this was the regular order, right? Always we were studying the expected value of something, then the variance of something. But now in between these two, we have a concept that we need to learn, which is covariance. Why? Because covariance is a necessary measure to calculate the variance of sums of random variables, okay? So in order to move to the third topic, we need to study the second topic first. Finally, we are going to give a short summary of the additive relationships between the spatial random variables. Actually, you know some of these. For example, you know that a binomial random variable is actually a sum of independent and identically distributed Bernoulli random variables. But when the time comes to there, we are going to explain them again and again. Now, let's start from the simple. What is the expected value of the sum of two random variables? So let's just say x and y are two arbitrary random variables, either discrete or continuous. It doesn't matter, okay? And they can be independent or not independent. Again, it does not matter. They are just two random variables, okay? The expected value of the sum of these random variables is always equal to the sum of individual expectations, respective expectations. Or in other words, if you're interested in calculating the expected value of x plus y, then you can simply calculate the expected value of the first random variable, then the expected value of the second random variable, and sum them up. So in short, expected value of the sum is equal to the sum of expectations. Now, the proof is very easy for that. Now, let's show the proof. And in order to show the proof, we are going to assume that both x and y are continuous random variables. So they have a joint probability density function, which is represented by f xy. And the expected value of x plus y is going to be calculated by integrating the interior function inside the expectation, which is x plus y, multiplied with the joint probability density function, and we are going to integrate that product. We are going to integrate the product of the function itself, x plus y function itself, with the joint probability density function through the whole domain of the distribution. Since this is a joint distribution, we are going to integrate that function first with respect to x and then with respect to y, and assuming theoretically that x and y random variables can take any real values. Therefore, we say that these integrals have boundaries from -infinity to +infinity. Now, of course, I mean, if the distribution of x and y, the joint distribution of x and y, has a specific domain, then we need to write down the boundaries defined in that domain here, right? But here, since we are speaking theoretically, we assume that there is no boundary for the domain, so these random variables can take any real values. Therefore, we basically run a double integral, first with respect to x and then with respect to y, of the function inside the expectation multiplied with the joint probability density function. Now let's do our tricks. Let's use mathematics and do our tricks. Now, how come this expected value of the sum is equal to the sum of the expectations? Now, because the joint probability density is a common multiplier for x plus y, we are going to distribute that multiplier over the summation, and we will have the integrand as x times the joint PDF plus y times the joint PDF. Then you know that the integral of the sum of two functions is equal to the respective integral of the sum of the respective integral of these functions. Therefore, we can run these integral operations first for x times joint PDF, then for y times joint PDF. And in the first integral, I am going to do this trick, and I am going to change the order of integral operators. So instead of first integrating with respect to x, I am going to integrate first with respect to y, and then x. I'm not going to do another change for the second integral. Now, if you check the first integral, the x multiplier here is considered as a coefficient for y operator, right? So it is simply, it's not a variable, it's just a multiplier for the integral operator y. Therefore, we can take this x outside the first integral. Then in the interior integral, we will just be integrating the joint probability density function with respect to integral operator y. And when you integrate the joint PDF with integral operator y, what you get is the marginal probability density function of x, right? If you remember the beginning of the 7th chapter, the first presentation file of the 7th chapter. Similarly, in the second integral, we have dx as the integral operator in the interior integral, and y is considered as a coefficient. Therefore, we can take y outside the first integral, and the interior integral will be the integral of the joint PDF with respect to dx operator, which is going to give us the marginal probability density function of y this time. Okay, so in the first integral, we have x times the marginal PDF of x integrated through the whole domain of x, and in the second integral, we have y times the marginal PDF of y integrated over the whole domain of y, and therefore the first integral is the expected value of x, and the second integral is the equal to expected value of y. And if you want to make the proof of this theorem for the discrete random variables, I mean, it is just going to be similar, except instead of integrals here, we will have summation functions, and instead of the joint probability density function, we will have the joint probability mass function. Now, we can generalize that formulation, that theorem, for a multiple number of random variables. Okay, so this proposition generalizes this situation. It says, say xi is a sequence of random variables such as x1, x2, x3, x4, so on and so forth until xn. So these random variables in this sequence can be any type of random variable, either discrete or continuous. They can be independent from each other, or they can be not independent from each other. It doesn't matter. They are just a sequence of random variables. Now, the expected value of the sum of these random variables will be equal to the sum of individual expectations again. So the formula that we have written here can also be generalized for more than two random variables. So this proposition is basically stating this. And in fact, we can repeat the further knowledge, repeat the knowledge of us in the earlier theoretical lectures. And we can say that, for example, if we have two arbitrary real numbers such as a and b, then two random variables such as x and y, the expected value of ax plus by is going to be equal to a times expected value of x plus b times expected value of y. Now, you know, the expected value of this sum of two random variables here is equal to the sum of the expectations. Now, I first distribute ax and by to their respective expectations. However, you also know that under the linear transformations or linear functions, the coefficient inside an expected value can safely get outside. So therefore, we can write this expression as a times the expected value of x plus b times expected value of y. Now, if we, instead of linear functions like this, if we have other type of functions for random variables, in that case, the expected value of gx plus hy, such as g and h are real valued functions of random variables x and y, in that case, we can separate the expectations. However, you know, we cannot take the functions outside the expectation, because we know from the 6th chapter that expected value of functions of random variables are not equal to the functions of the expectations. However, expected value of the sum of two functions will be equal to the sum of the expectation of individual functions. Okay, so we can do that. Now, we are just going to use our knowledge now. We are going to use our knowledge now to solve this question. We have two random variables, x and y. So the question gives us this information. The expected value of x was 5. The variance of x is 9. The expected value of y is 4. And the variance of y is 4. And further, another information is the expected value of x times y, which is 15. Now, my friends, I am just going to show you something here. Now that we have mentioned about expected value of x times y, actually, we are going to calculate it in a few seconds, or I'm sorry, in a few hours, let's just say. But expected value of x and y is not equal to, it is not equal to expected value of x times expected value of y, my friends. So I can do this separation for summation, but I cannot do this equation for multiplication. Okay, so you'll realize later that expected value of x, y is not equal to the expected value of x times expected value of y if these two random variables are not independent. Okay, so we are going to come to that point, but I just want to warn you at this point, because you can easily see that the expected value of x is equal to 5 and the expected value of y is equal to 4, and the expected value of x times y is 15. Okay, so as you can see, the product of the expectations is not equal to the expected value of the product. Now, we have given this additional information because it is going to be necessary for answering some of these questions. Now, it says we are interested in calculating the expected value of joint functions of these random variables. For example, the first joint function is x plus 2y squared. So we are interested in calculating the expected value of x plus 2y squared. Another expectation that we are interested in is expected value of minus 2x plus 3y. So we have such expectations, and the question tells us this. Please provide the solution for these expectations, but if it is possible. Now, maybe with the provided information in the question, it is not possible to answer some of these expectations, give answers to some of these expectations, and we are going to see which one we can answer. Now, before that, before moving forward, let me tell you that we can also extract some additional information about the expected value of x squared and expected value of y squared. Now, if you remember, the variance of x is formulated as the expected value of x squared minus the square of the expectation. Therefore, in this question, I know both expected value of x and variance of x. Therefore, I can also calculate the expected value of x squared by using the sum of the variance and the square of the expectation. So if you sum the variance and the square of the expectation, you will get the expected value of x square, which is called the second moment of the random variable x. And it is going to be 9 plus 5 to the power 2, 5 square, which is 34. I can do the same for expected value of y square, which is variance of y equals to 4, plus the square of the expected value of y, which is 4 square, and that is equal to 20. So you see, I have expected value of x square and expected value of y square as an additional information. Now we are going to use all of this information and see if we can find answers to the expected values asked in the question. So for the first one, what I would like to do is to calculate the expected value of x plus 2y square. And for that, I am going to take the square of x first, then the square of 2y. Basically, I'm not going to explain your high school knowledge. I mean, this is the square of the sum of two variables, and this expands as x square, the square of the first term, plus two terms product multiplied with 2, which is 4xy, plus the square of the second term, which is 4y square. Now, you see we have three terms here, and we have a summation of these three components. I can rewrite this expectation of these three components, sum of these three components, as the sum of individual expectations. So I can say expected value of x squared plus, I can take this 4 outside the expectation, 4 times expected value of xy, plus I can take this coefficient also outside the expectation, which is going to be 4 times expected value of y squared. And the expected value of x squared is 34. Expected value of x times y was 15, and expected value of y squared is calculated as 20, and therefore the result should be 174. Now, in the second question, second part, we are asked the expected value of minus 2x plus 3y. What I can simply do is I can rewrite this expectation as minus 2 expected value of x plus 3 times expected value of y, and that is going to be minus 10 plus 12, a 2. Okay, so the second one was rather easy. Now the third one is minus 2x squared plus square of 2y, and square of 2y is equal to 4y squared. Again, I am going to do the same. I will divide this, separate this expectation of the sum of these two components as the sum of individual expectations, and I can further take the coefficients minus 2 and 4 outside the expectations. Hence, it will be minus 2 expected value of x squared plus 4 times expected value of y squared, and that is going to be a 12. Okay, so you see both in A and C, we required the calculation of the expected value of x squared and expected value of y squared. So I hope you understood why I have done these additional calculations, because they are required. Okay.